This is lecture video 31 and we will cover sigma notation and limits of finite sums in this section. In estimating with finite sums in the previous section, we encountered sums with many terms. And in this section, we introduce a more convenient notation for sums with large number of terms, which is the sigma sum and denoted like this. After describing the notation and stating several of its properties, we look at what happens to a finite sum approximation as the number of terms approaches infinity. Okay, so let's look at more details now. This is called as the sigma notation. Okay, this symbol is called as the sigma notation, and AK here is the formula for the k term, which depends on k. This is something depending on k, and here k is an index starting from 1, and this is the last terminal point for k. And this symbol is the Greek letter sigma. For example, let's put something depending on k here inside the sigma notation. For example, k squared, right? K from 1 to 4, let's choose an S4, k squared. So this notation means that you sum all the terms in the form of k squared from k equals 1 to 4. So you insert 1 for k, you insert the second index for k, insert 3, and now we are here. You see, this is the terminal point for k. Okay, let me give you another example. So let's put k cubed minus 1, where k is from 1 to 5. Then it looks like you will step by step insert these integers for k. 1 cube, okay, let's start k from 2. And then it doesn't need to start from 1. You can start your sub-index at any point you like, and it can finish at any point we like. So 2 cubed minus 1, this is the first term of this finite sum. Start 3 cubed minus 1, 4 cubed minus 1, and the last term will be 5 cubed minus 1, okay? Like this. So there are certain properties of this sigma notation satisfy. For example, it respects addition and subtraction. Okay, you can directly distribute sigma notation to addition and subtraction. Okay, let's give an example on this. Let's say you are creating a finite sum from k is 1 to 3, like 2 to the power k and k to the power 2. Normally, it looks like how? Just go through these indexes, like k equals 1, then k equals 2, and then k equals 3, which is the terminal point, 3 squared. What does this say? You can just distribute it over these two, right? So we can write it as, let's say, just rearrange the terms here, okay? 1, 2 to the power 3, and here we have 1 squared, another 2 squared, and 3 squared. I just rewrite the same thing, and look at what we have now. This is sigma notation from k to 3. What is it? It is 2 to the power k, and this part becomes k from 1 to 3, k squared. So you see, we just distributed the sigma notation over these two. You can do the same for the subtraction, like this, then all those notations will be minuses, so this you will get minus. For example, you can also give an example. I can also give an example for this. Consider this sigma notation where you sum up terms of this form from 1 to 4. So this looks like how? 1 cube, right? 3 times 2 cube, 3 times 2 to the power 4. And you can rewrite it as this, 2 cubed and 1 cube, 2 cube. I think this should be like, okay, it's 3 cube, and okay, let me fix it quickly, and the last term will be 3 times 4 cube. That's why, okay, this is 1 cube, 2 cube, 3 cube, and 4 cube. So you can turn back to sigma notation for this part as k from 1 to 4 k cube. So this means that you can take this constants which does not depend on k out from the sigma notation, okay? These constants may go out. Okay, ak is the term depending on k, but if you have constants independent of k, you can just take it out, okay? Like this. And here is the example of it. So one more thing. Let's look at this case now. Let's say we are summing up just 4s from k equals 1 to 5. This is the finite sum where we have all the time 4s for all indexes like this. 5 times 4, right? So it is in fact 5 times 4. We choose n as 5, so it is here, so proving this inequality. Okay, so let's move on. Another example. So we have an open form of a sigma notation. This is a finite sum, and we want to find its compact form written in the sigma notation form, right? So let's start with this one. Just insert your indexes for k, what you will obtain, minus 2 to the power 0, right? So first term is 1, minus 2 to the power 1. Second term will be minus 2. And third term, minus 2 to the power 2, which is 4. And similarly, if you insert all the k's up to k equals 6, you will obtain this finite sum, which is exactly this one. So part A, the sigma notation given in part A satisfies this finite sum. And look at part B now. This goes like minus 1 to the power 0, 2 to the power 0. So first term is 1. Then insert k equals 2. You will obtain, sorry, k equals 1. You will obtain minus 2. If you keep doing like this, like inserting all the integers for k from 0 to 5, you will obtain this. Plus 2 to the power 4, 2 to the power 5. So this also satisfies this expression, very same expression. So you can also write this finite sum in a sigma notation like this. But it's the last one. So if you insert k equals minus 1, the first term will be minus 1. Okay, let's choose another color. So minus 1, insert k equals minus 1. Then the second term will be 2. And if you keep doing this, inserting all the k's from minus 2 to 3, you will obtain this expression, which is the minus of the given expression, right? That's why this does not satisfy. Okay, let's move on. Here you see another sigma finite sum, and we want to find the result of it. This goes like you first insert minus 3 squared, okay, then minus 2 squared, then minus 1 squared. It is 4 like this, and the result is 14. Okay, let's look at this one. This time we will try to find a compact form of this finite sum. So look at the structure here. It goes like, okay, the denominator is always 5 and nominator is increasing. So if you can just put k here and run k from 1 to 5. So now there is only one difference between right and left hand side. This goes like minus, and this is always plus. So if you have some alternating finite sum, like for the first term, sign is minus, then it's plus, then minus. So this can be covered by putting minus 1 to the power k here, okay? So like that. And these are really nice formulas, let's say formulas, okay, which we will be using in a minute. Okay, this is the sum of integers formula. How do you obtain this? I can give you a very quick way of understanding this formula. Let's say you are summing up all the numbers from 1 to 100. So if you look at the sum of the first and last term, it is this, right? And you do the same. The previous number is 99, sum them up, and you will be doing like this for all the remaining parts, right? That's why the sum is kind of, this number appears here how many times? It appears as the number of terms here, which is in fact 100/2. So you see, you are summing up all the numbers from 1 to 100, and the result is given by this. So if this number is n, it goes like n times n plus 1/2, just like we have here. Okay, this is a quick way of understanding that. So let me also write it in the general case like 1 plus 2 plus 3 plus n, and this is in fact given by n times n plus 1/2, the sum of the integers formulas. But if you are summing up all the squares of these integers from 1 to n, then the formula becomes this one, okay? So n times n plus 1 to n plus 1/6, and if you are summing up the cube of the integers from 1 to n, you will have this formula. So let me write it also like that. Cube of all the integers from 1 to n, you are summing up the cubes, but the formula goes like this, then n plus 1/2 over square. Okay, so let's try to apply them here. I am summing up the cubes of numbers from from 0 to 5. So this goes like 0 cube, 1 cube, 2 cube. So the last term will be 5 cube. Okay, the first term doesn't have any effect, and I know how to sum those numbers up through this formula, right? The n is 5, so 5 times n plus 1, 6/2 squared, which is 15 squared. Okay, what if you are again summing cubes, but from k is from 3 to 15, not starting from 1? Okay, you can handle it. 3 cubed, 4 cubed, and all the way up to 15 cubed. And so normally if you would have the first two terms too, like this, these are the missing ones, right? If you would have also the first two terms, the formula would work like this. So it would be then 15 times 16/2 squared. But since they are missing now, you need to subtract them from the overall sum. So you can handle it like this. Okay, let's move on. This is another sigma sum, and we will be using this property of sigma sum. We are summing up constants from 1 to n, right? So we are summing up 4s. How many times? So this is for each k index, you write 4, nothing but 4. 1, 3, 4, 5, 6, 7, 8. So it is in fact how many times? 8 minus 3 plus 1 times, I guess. 1, 2, 3, 4, 5, 6. So 6 times 4 is the result. 6 is the number of terms coming from here. Okay, let's look at this one. For such sigma finite sums, you need to first do this computation inside it. So what do we have? 2k squared plus k. K runs from 1 to 7. Now, what we learned in the properties, you can distribute sigma notation over sum. It respects over sums. So it is then k is from 1 to 7, 2k squared plus k is from 1 to 7k, and another property now, the constants that does not depend on k can go out from the sigma notation. This is 2 times k is from 1 to 7, k squared, k is from 1 to 7k. Now it is time to use the formulas for sum of squares and sum of the numbers, right? Okay, so sum of squares formula goes like, okay, you remember it from here, squares, n plus 1 to n plus 1 over 6. N is 7 here. Okay, so I will be writing n plus 1 to n plus 1 over 6. Okay, this is the sum of squares formula, and sum of integers and n plus 1 over 2, right? So n is 7, 7, n plus 1 over 2, like this. Okay, here I will make a remark before continuing with Riemann sum. Okay, remark. Be careful that the sigma notation does not respect multiplication. It respects addition and subtraction, but it does not respect multiplication, which means that you cannot distribute the sigma notation over multiplication like this. They are not the same. For example, let's say you are trying to compute a finite sum of this form, ak, bk, k is from 1 to 3. Okay, let's put 1 to 3. Okay, a1, b1, a2, b2, a3, b3. And let's look on the other hand, this form, where you find the right-hand side from k runs from 1 to 3. Okay, then right-hand side is, this is what? This is a1, a2, a3, and this is b1, b2, b3, and obviously right-hand side, left-hand side is totally different from this expression on the right-hand side. Okay, this is an important remark, saying that sigma notation cannot be distributed over products. It cannot respect products, but it can be distributed over sums and subtractions.